Welcome to a realm where sustainability, innovation, and agriculture converge to create a harmonious ecosystem. In this video, we unveil a lineup of extraordinary machines and tools that are reshaping the way we grow food and raise livestock. Experience the power of vertical wind turbines, harnessing renewable energy to sustainably power farming operations. Witness the efficiency and precision of automated tomato harvesting robots. Explore the transformative potential of precision livestock feeding systems in optimizing animal nutrition. Discover the accuracy and effectiveness of crop sensing robotic weed control. Finally, delve into the world of advanced soil erosion control measures that safeguard precious topsoil. Together, they paint a picture of a future where agriculture is both productive and regenerative. Number 5. Vertical wind turbine. A wind turbine is referred to as a vertical wind turbine if the main rotor shaft is oriented vertically, meaning that it is parallel to the ground rather than at an angle. Vertical wind turbines have their blades placed in a vertical arrangement, as opposed to horizontal axis wind turbines, horts, which have the rotor shaft positioned horizontally. These horts are the most common type of wind turbine. Wind turbines that are vertical in orientation typically include a vertical rotor shaft with blades that can be designed in either a helical or straight configuration. Because of its vertical orientation, the wind turbine is able to harvest wind from any direction, which eliminates the requirement for your gears to track the direction of the wind. Because of this, vertical wind turbines are appropriate for use in urban areas or other regions with limited space and changeable wind directions. Wind turbines with a vertical axis provide a number of advantages over wind turbines with a horizontal axis. They take up a little footprint and their installation necessitates only a little bit of room. They are able to function effectively under wind conditions that are turbulent or irregular, including those that are typical in metropolitan locations. When compared to their horizontal equivalents, vertical turbines have a lower noise profile and a lower danger of bird strikes than their horizontal counterparts. There are a variety of designs and combinations available for vertical wind turbines. Some of these designs include helical, Darius, and Savonius designs. The Darius turbines have curved blades that look like an egg beater, and the Savonius turbines have a curved shape that looks like an S-shaped rotor. Both types of turbines are used to generate electricity. Wind energy may be captured more effectively by helical turbines thanks to their twisted blades. Number 4. Automated tomato harvesting robot. A tomato harvesting robot is a robotic device that is designed to automate the process of harvesting tomatoes from plants, also known as an ATHR, automated tomato harvesting robot. These robots have been custom built to recognize ripe tomatoes, remove them from the vine, and either place them in a container of their own or gather them for later use. Robots created specifically for the delicate task of picking tomatoes often include either a robotic arm or a specialized gripper mechanism designed to handle the fruit's unique characteristics. The robotic arm or gripper is designed to imitate the movement of a human hand. It does this by gently seizing ripe tomatoes and removing them from the plant without inflicting any damage. Vision and sensing technology are frequently incorporated into automated harvesting robots so that they can detect and recognize ripe tomatoes. These systems make use of cameras, sensors, or machine vision technologies to determine the ripeness of tomatoes based on their color, size, and other characteristics. Because of this, the robot is able to pick just ripe tomatoes while leaving the immature ones on the plant to ripen naturally. In order to move around in the greenhouse or field where tomatoes are grown, automated tomato harvesting robots utilize cutting-edge navigation and localization technologies. These robots could make use of global positioning satellites, GPS, computer vision, or other methods in order to precisely position themselves and maneuver around obstacles on their way to collecting the target tomatoes. Real-time analysis is performed by the vision and sensing systems of automated tomato harvesting robots to determine the quality of the acquired photos or sensor data. The data processing algorithms examine the tomato's color, shape, and maturity indicators, which enables the robot to make educated decisions regarding which tomatoes should be harvested. Number 3. Precision livestock feeding system. The process of optimizing and exercising control over the act of feeding livestock animals is referred to as a precision livestock feeding system. This system is driven by technology. The goal of these systems is to deliver accurate and individualized nutrition that is based on the particular requirements of individual animals or groups of animals. The collection of data on animal behavior, bodily condition, feed intake, and other important factors is often accomplished by various sensors and monitoring equipment, which are frequently included into precision livestock feeding systems. This information, which is gathered in real time or on a periodic basis, provides insights on the dietary requirements of the animals as well as their current state of health. Precision livestock feeding systems involve the utilization of automated feeding equipment in order to provide the proper feed ration to specific animals or groups of animals. This piece of machinery is capable of being configured to dispense predetermined quantities of feed at predetermined times or in response to predetermined signals from the monitoring devices. The development of accurate feed formulas for livestock is made possible by precision livestock feeding systems, which make use of sophisticated software and algorithms to analyze the dietary requirements of the animals. In order to improve the nutrient composition of the feed and guarantee nutritional balance, these systems take into account a variety of criteria, including the animal's age, weight, breed, production goals, and environmental circumstances. Precision livestock feeding systems make it possible to design personalized diet programs for each individual animal that are tailored to meet the requirements of that animal in particular. The system takes into account the data gathered from the monitoring devices and modifies the feed ration appropriately in order to satisfy the nutritional requirements of the animal. Number 2. Crop sensing robotic weed control. In crop fields, the usage of crop sensing robotic weed control refers to the employment of robotic systems that are outfitted with sensors in order to locate and target weeds. These robots make use of advanced technology to recognize weeds and selectively remove or control them. As a result, crop damage is reduced, and the requirement for herbicides is cut down significantly. A wide variety of sensors are utilized by crop sensing robotic weed control systems in order to identify and differentiate between crops and weeds. Cameras, lasers, and even infrared technologies are all examples of the types of sensors that fall under this category. The sensors collect information on plant features such as color, shape, size, and growth patterns, allowing the system to differentiate between weeds and crops based on their appearance. In order to recognize and categorize the weeds that are present inside the crop field, the collected sensor data is analyzed utilizing computer vision algorithms and machine learning methods. The software generates a weed map that illustrates the distribution of weeds across the field, as well as their density. During the process of weed control, the robot's actions are guided by the information in this file. The weed map enables the robotic system to autonomously target and treat the weeds, hence decreasing the amount of harm caused to the crops that are located nearby. For weed control, the robot is equipped with a number of different ways, including mechanical removal, the delivery of herbicides with pinpoint accuracy, and heat treatment. The accurate targeting helps to cut down on the amount of herbicides that are needed and reduces the effect on the overall crop production. In the field, crop sensing robotic weed control systems are intended to function on their own without human intervention. Using GPS or one of the other several localization systems, they navigate across the rows of crops. The robots are capable of adapting their behavior based on data received from real-time sensors, and they may be programmed to follow particular pathways or target particular regions. Number 1. Advanced Soil Erosion Control Measure. In the context of agriculture and the environment, the term Advanced Soil Erosion Control Measures refers to novel procedures and practices that are implemented to reduce the effects of soil erosion and to prevent its occurrence. The topsoil, the fertility of the soil, and the structural integrity of ecosystems are all going to be protected thanks to these actions. To practice contour farming, one must first till the soil and then plant crops following the natural contours of the ground. This method serves to slow the flow of water across the slope, which in turn helps to reduce erosion by allowing the water to penetrate the soil, rather than washing the sediment away. Creating a sequence of steps or terraces on a steep slope requires terracing, which entails constructing level platforms on the hill. These terraces help to break up the slope and slow down the speed at which runoff water travels down the hill. In addition to this, they offer flat regions for crop cultivation and retain soil on each level, so reducing the amount of erosion that occurs. Plowing and tilling the soil less frequently is one of the conservation tillage strategies that reduces the amount of soil disturbance. Utilizing this method helps to preserve the structure of the soil, boost the amount of organic matter present, and improve water infiltration. Additionally, reduced tilling leaves crop leftovers on the surface of the soil, which provides an extra layer of protection against erosion. When land is left fallow, or when cash crops are rotated out, protecting the soil from erosion by planting cover crops such as legumes or grasses is an important part of sustainable agriculture. Cover crops create a thick layer of vegetation that acts as a shield against the damaging effects of wind and rain on the top layer of soil. In addition to this, they improve the structure of the soil, cut down on drainage, and provide organic matter to the ground.